It's a tale of four mathematicians who worked on the same problem, but in very different historical periods. First of all, we have at the top of this slide Carl Gustav Jacobi, who was active during the reign of the Prussian monarchs in the first half of the 18th century. Then we have David Koenig and Diego Echevarri, who did their research in Hungary in the first half of the 20th century, when it was governed by Admiral Horthy, the Germans, and the Russians. And last, myself, who started my career in post-war United States during the period of Eisenhower, Nixon, and McCarthyism. These four mathematicians are connected by one problem and an algorithm called the Hungarian method, which solves the mathematical problem that's known in operations research as the linear assignment problem. Our tale begins in 1953, and it will move forward and backward in time. I spent the summer of 1953 at the Institute for Numerical Analysis at the University of California in Los Angeles. Although I was supported by the National Bureau of Standards, I had no fixed duties that summer and spent most of the summer working on the traveling salesman problem and the assignment problem. It's important to establish the historical context of this work. Linear programming was only about 5 years old. And in the summer of 1948, David Dale, Al Tucker, and myself formed a project to study the relationship between linear programming and zero-sum two-person games. An important side product of this project was the first rigorous proof of the duality theorem for linear programming. In the summer of 1950, Tucker and myself presented the first paper on nonlinear programming. Although the simplex method was being programmed for the new electronic computers of the day, the possibility of special algorithms for special problems like the assignment problem seemed to be a real possibility and opportunity. Happily, there's a splendid new book that gives a detailed history of the sources of the assignment problem. You can see that one of the co-authors is the chairman of this session. He didn't pay me to put this plug in here. But I'll give you the full detail. It was published by Sciam last year, and you'll find it a great book. It gives a detailed history of the origins of the assignment problem and its subsequent development. That allows me to give a very condensed treatment of the problem here. It can be stated very simply as follows. I'm glad I'm controlling the computer myself. What is the assignment problem? Well, in the form I want to discuss today, the data are the entries of the square matrix, call them Rij. And then the problem is to find n entries, one in each row and column, no two in the same row or column, such that the sum of the entries is a maximum over all such assignments. A natural interpretation is Rij is the rating of individual I and job j, and we want to maximize the total rating sum. Why is it a linear program? Well, first of all, we can represent the assignment by matrices which are known as permutation matrices, using 0 or 1. 1, if you're going to assign the entry in ij, you'll find a 1 in position ij. I've given you an example of such a permutation matrix for n equals 3. 1, 1 in each row and column, the rest zeros. Geometrically, these matrices are points in an n-squared dimensional space. And since our object is to maximize a linear function, the rating sum, we get the same answer if we maximize over the assignment or if we maximize over the convex hull of these permutation matrices in n-squared space. And here we're helped by a theorem which nobody credits to Koenig, but he really did it. It's always credited to Garrett Birkhoff in a paper of 1946, but it's really implicit in the work of Koenig himself. The theorem says the convex hull of the permutation matrices is very simple to describe. They are the doubly stochastic matrices, matrices with non-negative entries and row sums 1 and column sums 1. So this allows us to state very easily the linear program which is equivalent to the assignment problem. This problem is maximize the sum of Rij times Xij over all I and j, subject to the constraint that every Xij is a non-negative number, and the sum on I for each j is 1, and the sum on j for each I is 1. That is, maximize the rating sum over the doubly stochastic matrices. The dual program is equally easy to describe. This is a minimum problem with one variable ui for each row and one variable bj for each column. And here we want to minimize the sum of the ui plus the sum of the bj, subject to merely ui plus bj being greater than or equal to Rij for all I and j. I'll often use in this lecture a matrix W, whose entries Wij are equal to ui plus bj minus Rij. And so, stated this way, the Wij have to be non-negative. Now, I knew all of these things in 1953 in the summer. And you have to imagine my surprise when I encountered the following theorem in a classic book on graph theory published by David Koenig in 1936. I was reading a German version which was published in the United States by the Alien Custodian Act. The book was not translated into English until 1990, which is amazing to me. Well, the theorem that I read in this book was the following. For a graph G, let M be the minimal number of vertices with the property that every edge of the graph ends in one of these vertices. And let N be the maximum number of edges you can choose, no two having a common endpoint. If G is a bipartite graph, then M equals N. You'll recall a bipartite graph is a graph in which all the vertices can be partitioned into two sets, and every edge goes from the first set to the second set. Now, a bipartite graph can be represented by a matrix in which the vertices of one set of the rows and the vertices of the other set are the columns. And we'll enter a 1 if an edge goes from vertex I to vertex j in the position ij. Then we have a restatement of Koenig's theorem. Given a square matrix with entries 0 and 1. The maximum number of ones you can choose, no two in the same line, row or column, is equal to the minimum number of lines needed to cover all of the ones. I'll repeat that. The maximum number of ones you can choose with no two in the same line is equal to the minimum number of lines, rows or columns, needed to cover all the ones. This is an astonishing result. I think it's hard to time exactly when Koenig discovered it, but it was possibly as early as 1916, but it surely lectured on it in the 20s and at the end of the 20s. First of all, it's an example of a linear programming duality, proved decades before Danzig formulated linear programming. It's also the first example of a problem in combinatorial optimization that was solved by Koenig with a constructive algorithm that was polynomial, a good algorithm. So you can understand my excitement when I went back to my college, Bryn Mawr College, at the end of the summer, knowing that all one had to do was to reduce the general assignment problem to a sequence of 0-1 problems. You had a good algorithm for solving 0-1 problems, but how should we reduce the general problem to the problem that Koenig had given a good solution for? But before I tell you the rest of the story, I must tell you who was Daniel Koenig and a bit about his life. First, I shall teach you how to spell Koenig's name correctly, something that's seldom done in the literature. The diacritical mark over the O in Koenig is not umlaut. It's not two periods. It's the Hungarian double acute sign. And this is a letter from Daniel Koenig saying, this is how I spell my name. I spell it with a double acute, not an umlaut. Here's a picture of him as a young man. He was born in Budapest on September 21st, 1884, to a family of Jewish origin, but he was baptized as a Christian, which becomes important later in the story. His father, Julius Koenig, was an important mathematician whose influence on Hungarian mathematics lasted into the beginning of the 20th century. I think Julius is noted mainly for an incorrect proof he gave of the continuum hypothesis at one of the math congresses in the 19th century. Danius, on the other hand, was a boy prodigy, winning highly competitive prizes and publishing his first book on mathematical recreations when he still was a student in a Budapest gymnasium. His further mathematical training was done half in Budapest and half at Göttingen, where he was introduced to topological concepts by Minkowski. Having finished his studies in 1970, he worked as a demonstrator at the Polytechnical University of Budapest, which I'll abbreviate later in the lecture as BME. He remained there until his death in 1944, attaining the rank of professor in 1935. Of course, if Koenig's name is known to you at all, that's what he looked like somewhat later. It's very hard to find a picture of Koenig. I've only located two of them. This one is excerpted, cut out of a group photograph that was taken in Szeged in 1928. I've hunted high and low and not found another available picture of Koenig. If his name is known to you at all, it's known through graph theory. The book which I was reading in 1953 was the only full book-length treatment of graph theory that had appeared before Claude Berger's book in 1958. Through his lectures, Carnegie inspired an entire generation of Hungarian mathematicians to work in graph theory, including Egervari, Erdős, Turan, Galai, and many others. One can see a direct line of influence from Carnegie through his student Galai to his student Lovas, the current president of the International Mathematical Union, and the whole Hungarian school of combinatorics. Some sources tell of Carnegie's efforts to help persecuted Jewish mathematicians. I've been able